Okay, the second speaker today is Mikael de la Salle, who will talk about the HIher-rank lattices and uniformly convex Banach spaces. I said HIher-rank, you wrote
yes.
HIher-rank.
I wrote, it's a typo. It's a typo.
No, it's not. There are people like that, the people who do like that. I checked it recently because I wrote a paper. Some people do like that, some do that, but somehow I prefer HIher-rank. So I allowed myself to change it.
I don't care. So. Okay, let's make you happy. Thank you very much for the introduction. I'm very happy to be here. It's my second visit here. Last visit was 8 years ago for the first iteration of this conference. I checked and I talked about something completely different at that time. I talked about a result that I had with Romain Tessera, but it was more in combinatorics and well, graph and so today it's more it's the main object I'm talking about. It will be high-rank lattices. So these are groups that do not like non-negative curvature. So these are we have some results that say that they. Well, let me state a theorem. The theorem of today. So it's a theorem. It's due to many people, and the last case is a joint work with Mikael for Tim Delat. So the theorem says that well, let's A to be either the ring of integers or some rings of polynomial over a finite field, and gamma to be the group of 3 by 3 matrices over A. So I just write it like this in case there is one person in the audience who does not already know what a high-rank lattice is. For those who know, you can just take gamma, take any lattice in any simple algebraic group over a local field with a rank at least 2. Okay, and the theorem says that any action of this group by isometries on a uniformly convex Banach space has a fixed point. Okay, so what is uniformly convex? So what is uniformly convex? So I draw a picture. A Banach space says uniformly convex. If I draw the unit ball and say it's something that only depends on its 2-dimensional subspaces, so I can draw it on the board. And it says that if I take 2 points in the ball that are far apart, then their midpoint is also far apart from the boundary of the ball. So let's put that in formula so for every epsilon positive, there exists delta positive, such that for every x, y in let's call it x, this Banach space, for every 2 points of norm less than 1, if I assume that they are far apart, meaning that the norm of the difference is at least epsilon, then we have that the midpoint, x plus y over 2, it has norm less than 1. This is exactly putting in formulas what I had written here. Okay, so the theorem is, I think it's clear. So it says that if this is a convexity assumption or curvature assumption on the Banach space. So it's meant to, so examples, the one for which the epsilon delta dependence is the best, these are the Hilbert spaces. And the fact that these are the best for Hilbert spaces is some very fundamental result due to Dvoretsky in Banach space geometry. So the most uniformly convex spaces are Hilbert spaces, and in this case, this is due to Kazhdan. So Kazhdan and I think the norm. So well, formally, you all recognize, I guess, if you take a Hilbert space and if you take a gamma, which is a countable group, the property that such a countable group, any action by isometries on a Hilbert space has a fixed point. This is, by theorems of Delorme and Guichardin, this is equivalent to Kazhdan's property T. And therefore, the fact that this theorem is true for this gamma is equivalent to Kazhdan theorem that these groups have property T.
Your theorem is for HIher-rank lattices only in simple?
Yes.
Not in semi-simple, irreducible in product of rank?
No, it's false. It's false in products of rank 1 because it does not have property T, so it does not have, even for Hilbert spaces, it's false. So of course you can, well, you can take a lattice in a product of simple groups of rank at least 2, but no, products of rank 1 groups, this is not a problem in the proof, it's a problem in the statement. The statement is false for this kind of higher lattice. Okay, so for the most curved spaces, Hilbert spaces, this is the very classical result from the 60s. If you take LP spaces with P in the range where you exclude 1 and infinity, then there are some classical inequalities that show that these spaces are uniformly convex. And these inequalities are usually, in my opinion, the easiest way to prove that LP spaces are, well, it's one way of proving that Hilbert spaces are reflexive, that LP spaces are reflexive. And so in this case, this is due to Bader, Uri Bader, Alex Furman, Sarik Gelander, and Nicolas Monod. So from almost 20 years ago. Actually, when they proved this theorem, they already also conjectured that the general statement should be true. And I will explain another motivation apart from the fact that it's true for LP spaces. Also, if in the polynomial arithmetic case, this is due to Laforgue. Vincent. For this statement, it's due to Laforgue, and if you take any high-rank lattice over a non-Archimedean local field, this is a work by Laforgue and another work by Liao that gives that. And in the integer arithmetic, or for lattices in Lie groups, in groups over Archimedean fields, this is a new result by Tim Delat and myself. And so the statement is due to Tim and myself, but there is it follows a breakthrough by Oppenheim, by Isaac Oppenheim. I will say a bit more probably later what he did and what we do and how things, what are the ideas. Maybe I will use the board that half of the room cannot see to explain one motivation, why in the theorem we need to have some curvature assumption on the space. So let me give examples that are, the examples here, they are all deep theorems. The examples that are here are maybe exercises. So if we take gamma, which is let's say a finitely generated group with finite generating set S, then actually we can make gamma act on the set of elements in L1 of gamma. So L1 of gamma is the set of functions from gamma to the complex number that sum to, so that the sum of the absolute values is finite. And I take the subspace where the sum is equal to 1. So it's an affine space. It's not a linear space because 0 is not there, but as an affine space, as an affine metric space, it's just L1 0 of gamma. L1 0 is the set of functions so the sum is 0. Okay, so gamma acts on L1 by translation. It preserves this condition, so it acts on this space. And, well, this is it acts by isometries on this affine known space, and it does not have a fixed point unless gamma is infinite. So without fixed point, if gamma is infinite. Okay, so we know that the theorem there cannot be true for spaces of the form L1 because, at least for L1 0 it's false because we have counterexamples. So this rules out some of the. This explains why we have to put some geometric assumption on the space in order to hope at least that the theorem there is true. There is another phenomenon that is even more in contradiction with the fixed point property. So we can consider gamma. It also acts in the natural way on the set of functions of the form f plus the word length. So this is the absolute value in text S is the word length with respect to the finite generating set S. Okay, so this as an affine space is just an infinity of gamma. Okay, but the action. This set of functions, I see them as functions on gamma, from gamma to the complex number. The group acts on this space by translation, by precomposition, and this action is proper, meaning that the distance between gamma x and x, so the distance is the distance in this affine space. This goes to infinity when the word length of gamma goes to infinity. So of course it's even. So it's an action by isometries on an affine space where the metric map is proper. So of course it's very far from being isometrics. So these two examples say that you have to rule out spaces of the form L infinity or L1, and the most naive way of doing that incorporates all the LP spaces in this range is the uniform convexity thing. Because, of course, I should say that it was implicit in my mind. So L1 spaces, the unit ball looks like this, so it's far from being uniformly convex. And L infinity, it looks like this, so the balls are not uniformly convex. So so this explains why you need some geometric assumption, and indeed the theorem there confirms that it's in. So actually the way the way people have tried to attack this question is, since the case of Hilbert spaces has been known for almost 60 years now, so we have had proofs that work for Hilbert spaces, and in time people have found new proofs of property T for groups like this, and the game each time is to try to see if the proof that is usually designed for Hilbert spaces, it can be adapted in a more geometric setting. In a more geometric setting where you only need this geometric condition on the unit ball and not more properties of the Hilbert spaces. So actually, this is exactly what Bader, Fuhrman, Gelander, and Monod did in their paper in 2007. They looked at the standard ways of proving property T, which I like to. So there are many standard ways of of proving property, but I like to summarize them all together by saying that the basic idea is SL2 reduction. So meaning that or another way of saying is rank 1 reduction. So this is, the theorem deals with groups of the form SL3, and the standard ways of studying groups of the form SL3 or higher rank groups is to study all the SL2s that live in SL3, study how these different copies, they live inside, they interact, prove something interesting about SL2, and then if you're smart, you can get this kind of result. This is SL2 reduction. So you do the analysis in rank 1 subgroups, and then you promote this local analysis to a global result that takes this form for actions on Hilbert spaces. And as I said, Banach and Claude managed to follow this strategy for LP spaces, and the reason why they managed to do it, and not for general Hilbert spaces, Banach spaces, is that we know, thanks to Banach and Lamperti, so not reason for the 30s, all results from the 30s, we know exactly the structure of the isometric group of LP spaces. Essentially, you can, if you don't know this Banach-Lamperti theorem, you can guess it. The proof is difficult, but it's easy to guess. So isometries of LP spaces, you can multiply by a function of modulus 1. This has not changed the LP norm. You can also precompose by some transformation of the measured space, underlying measured space. If this transformation preserves the measure, you just precompose. If this transformation only preserves the measure class, you correct by some correct power of the Radon-Nikodym derivative, and you get other isometries of LP spaces. And Banach explained us in the 30s that these are the only isometries. And so, in a way, this reduces this geometric question to a measure or ergodic theoretical question, and for this kind of questions, the tools from SL2 reduction work very well. Okay, and so this was the standard about the standard. Now Laforgue's proof, it's again a reduction, but it's a rank 0 reduction. What I mean by that, rank 0 is the same as compact. So you look, you work with SL3, actually not of polynomial, but some completion of the polynomials to get actually on the ring of Laurent series, because this is a nice locally compact field. And on that, you have SL3 of this field, you have these maximal compact subgroups. You do some analysis on these maximal compact subgroups. You understand how these maximal compact subgroups live inside the whole group. And it turns out that thanks to some very deep work of Jean Bourgain from the 80s that told us some very non-trivial facts about the behavior of the Fourier transform on abelian or nilpotent groups, Vincent Laforgue was able to obtain this theorem. Unfortunately, the strategy should work in the real case, or in the integer arithmetic case. I've devoted almost 10 years of my life to trying to prove that, and so far I have failed. So the rank 0 reduction should work, but there are some technical obstacles, and the main one being that Jean Bourgain has passed away. So we have to find a way to do some analysis in the to generalize in the spherical case some of the results by Bourgain. But okay, so still the result is true, and the way this is proved, it's again by some kind of reduction, but it's nilpotent reduction. So I think it's clear what I mean by that now. So we will restrict to nilpotent subgroups of the underlying algebraic group. We will do some analysis with actions of nilpotent groups on uniformly convex Banach spaces. We will exploit how these nilpotent subgroups, they live in the ambient group, and we will get the result. Okay, so that's...
But this works also for compact lattices?
Yes. Yes, you take any lattice in any product of simple groups of rank, each of them having a rank at least 2. So it works, and the way it, yes, I phrase it in this way just not to have to write all these hypotheses, but it works for any lattice. And anyway, it will be clear right now because actually, now I will explain the proof. So the first step, this is for me, it is standard, but I think it must, somebody had to have this idea at some point before it became a standard ID. The first step is induction. So here we reduce to the theorem for gamma replaced by SL3 of R or SL3 of Q. Or actually, in a way, it's of a ring of Lorentz series. Okay, so you take the... It turns out that these groups, they are not just groups, they are groups that live, they are arithmetic groups living in this kind of algebraic groups, and they are finite covolume, that's essentially Minkowski, I guess. And there is some induction procedure that says that, okay, if you are able to prove the theorem for this group, then you obtain, by this induction procedure, the theorem for all its lattices. And this is standard, but it uses some deep work. In particular, it uses it relies heavily on the work by Alex Lubotsky, Moses, and Raghunathan on the fact that these groups here, even though they are not co-compact lattices here, they are embedded in this group in a quasi-isometric way, which is a non-trivial statement.
Now, does this use arithmeticity or is that irrelevant?
Yeah, well, yes. Lubotsky Moses Raghunathan theorem uses arithmeticity. Yes.
But is that the only use of arithmeticity?
Yes. And for SL3Z, this is easier. The proof is a short compte-rendu note that is very easy to read at least. And that's the only way. Actually, formally, it only uses that gamma. If you take any finite volume subgroup that is quasi-symmetrically embedded in the group, then the proof works. But you need to know that all lattices are quasi-symmetrically embedded, and this uses arithmeticity. Okay, so in a way, we have gained something because we are working with countable groups that are in a way well. They do not have so much structure as the algebraic groups that I wrote here. In particular, we have we will see that. Okay, then step 2, that works both ways. So we construct a sequence μn of probability measures on, well, let's call these groups G. So there are two cases. G is either SL3 of R or SL3 of the field of Lorentz series. I wrote P, but I meant Q. Okay. I consider probability measures on G. When I wrote the subscript 1, I mean with first moment that is finite, such that if we take x0 in X, so here we have the group G that acts by isometries on X, which is a uniformly convex Banach space. So the goal will be to construct a sequence of probability measures, so that if I start with any point, and if I average with respect to this probability measure, so if I denote mu n dot x0, this is by definition a notation that I will use a lot. It's the integral of g x0 d mu n of g. Then we have that this sequence is Cauchy, and 2 is almost G invariant. So the first part will be hard and the second part will be easy. So if you can show that this sequence is a Cauchy sequence, and since we are working in the Banach space, it will converge. So saying that it's Cauchy is just another way of saying that it converges. And the fact that this sequence of points are almost invariant by G says that the limit which exists by the first point will be invariant by the group. And so, but I express it this way because actually the way you prove that it converges is exactly proving that it satisfies the local moves do not change a lot, and you really prove the Cauchy criterion. Okay, and the way you prove that it's Cauchy is exactly by reduction to subgroups of G. So if we were following one of the classical proofs of SL2 reduction, then we would study we will prove that this is Cauchy by reducing to SL2 subgroups inside SL3. If we were following Laforgue's proof, we would restrict to compact subgroups, and in the new proof that originates from Oppenheim and that we developed further with Tim, we reduce to nilpotent groups. And from now on, since the time is not so long, I will restrict to only the nilpotent reduction. So from now on, we take G to be SL3. Okay, and now I will consider H to be the subgroup of upper triangular matrices with 1 on the diagonal. Okay, so this is a group generated by 2 copies, 3 copies, well, it's generated by 2 copies, but I write 3 copies of okay, where, well, x of t, this is just what I would prefer to write x1, 2 of t. This is just the matrix where I put t in the 1, 2, and 3, and 0 everywhere else. Okay, y is x 2, 3. And z is x1. Okay, so we indeed have that, as the notation suggests, this subgroup Z is just the center of H. Okay, and maybe just to remind you the commutation relation, if I take the commutator of x of s and y of t, this is just z of st. Okay, and so let's try to make this second step a bit more precise and tell you exactly what is these probability measures mu n, what they are. Okay, so let's do that. So let's introduce some notation. I will denote if A is a real number, I will denote gamma A. This is just the Gaussian probability measure with variance e to the 2a. This is a probability measure with first moment finite on R. Okay? So this is just the usual Gaussian probability measure, centered probability measures on R that for some reason, I prefer to parameterize it by the 1/2 of the log of the variance, but okay, that's just a parameterization. Then I will define a new ABC to be just x of gamma A convolved with z of gamma B convolved with y of gamma C. Okay, so just let me explain what I mean. X is a homomorphism from R to H. So X of a probability measure on R is just the push forward of this probability measure by this homomorphism. So this is a probability measure on H, this is a probability measure on H, this is a probability measure on H, and I just take their convolution product. When I have probability measures on a group, I can take the convolution. Okay, so this is again a probability measure with finite first moment on H. Okay, and you see Z is the center of the group H, so I choose to write it this way, but I could have put the Z before or after, it would not change anything. But X and Y do not commute. So I might, and actually I will have to consider also the probability measures where I take the only different order that I can. So I put tilde on it, new tilde A, B, C. It's just I first put Y, then I put Z. This is not important where I put it, but, and then X. Okay, from now on, I forget the convolution product of probability measures. When I write the product of measures, I really mean the convolution product. Okay. And so these are probability measures on H. And now I will define out of these probability measures on G. Now the notation becomes slightly more heavy. So if I take A, B, C, D, E, F, so these are all real numbers, then I will consider, and actually the notation makes sense for all real numbers, but I will only consider them for positive real numbers. So I will define U A, B, C, D, E, F as the probability measure x12 of gamma A. So I will, for this I need a backup. So x32 of gamma B, x31 of gamma C, x21 of gamma D, x23 of gamma E, and x13 of gamma F. Okay, and let's see on a picture what we are doing here. So let me write the standard A2 root diagram. So this is the, so it's just I cut the space into 1/6 of a plane. I will put all the roots corresponding to these groups as it is in the usual way. So these are the okay, and the algebra that is behind exactly says that on this diagram, if I take 3 consecutive vertices, they will generate a copy of H inside SL3R. Okay, so for example, if I consider these 3 vertices, this, and this, these are exactly the standard embedding of H into SL3R. But if I take any other 3 consecutive vertices on this diagram, I still have a copy of H. And what I did here, I choose one of the roots, one of the vertices here, and I followed this diagram in some order, and I just, okay, first I have x12, then x32, etc. Okay, this is the explanation for this formula. And again, you know, so there is some reason why I want to follow it in the root order, but I could have picked another, I could have followed this cycle in the other direction, and this gives me something else that I also need to consider. I denoted it by mu tilde A, B, C, D, E, F. And this is, for some reason that will be apparent in maybe 10 minutes. I will not start exactly from the same point, but I will start from this point here. Okay, so I start with x31. Then I take x32, etc., up to x21 of gamma. Okay, and okay, and then now I will define mu n to be just mu n. Okay, so I introduced lots. Actually, the set of these measures are parameterized by r to the 6, 2 disjoint copies of r to the 6, but I only need for the big picture of the proof, I only need to have one sequence, but so it will be this sequence here. But my goal will be now to explain you what can you say about the actions of H on uniformly convex spaces, and then what you can say, how this can be used to say something for G. Okay. So actually, the most important ingredient, I already said it to you already, it is that if you take any 3 vertices, neighboring vertices here, you have a copy of H. The second ingredient that will come later, which is also of the nature of what can we say about the embedding of H into G. So the fact 1, which is something that is very easy, is that if you have if you write G to be, so G is a compactly generated group, so let me choose Q, a compact generating set of this group, and then I have that the word length of Z of T with respect to Q, this is of order log T. Okay, this is the polar decomposition. And this is much better than, okay, what is the word length inside H? This is just something like square root of T. So the fact that if we look at H inside this semi-simple group SL3, well, it will be very important that it's exponentially distorted. Okay. The second step, which is, well, for me, it's an incarnation of the fact that H is amenable, or it's a way of proving that it's amenable. If it's that, okay, if we compare, okay, we have these 2 measures, nu and nu tilde, and if we take nu ABC and nu tilde CBA, you have the same. It's the same factors, but in a different order. With and this is the Z is the center, and this I claim that this in total variation this is less than e to the A plus C minus B. So this is good if B is much larger than A plus C. Okay, so what is this saying? This is very simple. It's just saying that okay, X and Y, they do not commute. But when you take a commutator, what you see appearing is Z of ST, of the product. And the measure gamma B is a very good, it's an almost invariant measure on R. if we take a Gaussian with very large variance, it is a very good Reiter sequence of probability measure. It's something that expresses the amenability of R. And so if B is very large, saying that this is a measure that is very much Z invariant, then when you force to take X and Y to make them commute, this will not be affected in the total variation distance if you have a measure of, if the measure on the center that you put is enough invariant, and that's exactly what's happening here. Okay, this is very simple exercise. Just write down what I said, and you get that. And the third step, this is far from being as simple. So far there was no Banach space involved. So now we will use that we have a Banach space. We will use that the space is uniformly convex, and we'll get a conclusion about the actions of Z. So there exists some constant C and Q that is strictly less than 1 that depend on X, and they depend on X through the epsilon delta dependence that I have as in the axioms of uniform convexity, such that for every X in my Banach space X, for every ABC real numbers, and also B prime, and if we assume that B and B prime, they are both less than A plus C, then we can compare nu ABC of X and nu A B prime C of X. So this is the norm. This is a point in X, this is a point in X, so I compute the distance in the Banach space X, and we get that this is less than some constant Q to the square root of A plus C minus the maximum between B and B prime times 1 plus B minus B prime times the displacement for t less than e to the b of z of t x minus x. So this was a typo, it's a plus c. Okay, so this, let's have a look at that. So this inequality says that, okay, if we take the average along the orbit of x with respect to the measure nu ABC, and then we do the same except that the variance corresponding to the center, the b, is replaced by b prime, where b and b prime are all both small relative to the sum of a plus c, then we get some bound that is small. What is important here is is q. So it's not important exactly what it is, but what is important is we have something that is strictly less than 1 to some power that will become very large. Okay?
So you said the inequality is good if b is large, and then you use it for b small.
Okay, so actually I have two inequalities. The fact 2 is one inequality that is good with b is large. The second inequality is good when b is small. And indeed, that's a problem. So these two facts together, they do not tell you anything interesting about actions of H. But what we will do, we will use, as I said, that in G you have lots of copies of H, and if you combine these inequalities that live in different worlds, you will be able to have something meaningful at the end. Okay, and again, another aspect in this inequality that you have here is that here, you know, maybe I will write it here. In general, so if we have any group that acts on a space X by isometries, then what we have in general is gamma x minus x. This is less than the word length of gamma times the maximum for S in S of the displacement of the generators. Okay? And here you see that here you are asking how much z of t is moves x when t is less than e to the a plus c. So if you were working with just a plain representation of the nilpotent group H, this would be very bad because you have that z of t is over the square root of t. So this would be of order e to the a plus c over 2. And here we have some q that you don't control to some power square root of a plus c minus something. So these two combines is very bad if you don't know a priori that your action of H comes from an action of G. Because now, if you use the exponential distortion of that, then this becomes a plus c if instead of e to the a plus c over 2. So this will be some logarithmic order terms times some quasi-exponential order. So that's it. So, but this is, let's forget about the details. What you need to remember now, I think I have 5 minutes. So in the 5 minutes remaining, I will explain. Okay, you have these two things. When B is much larger than A plus C, you can exchange the order. And when B is much smaller than A plus C, you can tune a bit the parameter of the center. And let me explain you now how you can combine these two facts together to get exactly the Cauchy criterion. Okay? So I will do that on a picture. Unfortunately, since the space of parameters is 6-dimensional, my picture will not be very clear, so I prefer to I don't know what's the best way of drawing something 6-dimensional on a plane, so let's okay, so this is a mirror. So on one side, here you have R6, and here you have its mirror image, R6 tilde. Okay? Now let's start with N. Okay? So I will draw it like this. Okay, I have 6. This is the first N, the second N, etc. So they are all at the same level. And I want to use fact 3. It tells me that whenever I take 3 consecutive letters in this 6-letter word, let's say, for example, let's say this one, I'm allowed to change a bit the middle one, because the middle one corresponds to the center, as long as the new B prime is much smaller than the sum of the two. Okay, let's do that. Let me take a picture maybe, a color. Okay, so let's do that. So we are allowed to move this one a bit. So we get, this is a bit larger. Okay, now I do the same. I will increase this one a bit. I can increase it a bit more because what we need is that the sum, this must be smaller than the sum of this plus this. And this is a bit larger than before, so I'm allowed to move it a bit higher than I was just before. So I get something like this. Okay, now I'm in a better situation because this one, I can even move it even a bit more because I have gained something on its right. So I guess I get something like this. And now I'm in a situation where this is much higher than this, so I can move it even further. So I can move it very high. This one I can also move it very high. So at the end, I guess I get this this, and this. And now, okay, this I can take it down as much as I want because I'm still in a good situation. So I get this. This is very high, and this is a bit higher, but not too much. This is n prime. This was n, and this was n prime. N prime that is slightly larger than n, but not too much. Okay, and now I'm in the situation where I can apply fact 2. You know, the thing in the middle, I've put it high enough so that it's much larger than the sum of the two here. So I'm allowed to do the mirror image here and here. But if you do the mirror image of both these, so you know, you have here, you have this upper triangular and this lower triangular. I can, if I do them a mirror image of both, it's exactly saying that I'm following this new tilt, the circle in the other direction starting from here. So it means that using this mirror, I can get to the situation where I have this, and this. Okay, but on the mu tilde side. And now I can follow, you know, the picture that I did on the left. I can do the same upwards on the other side of the mirror, and I can get, you know, I can tune everything so that at the end, you know, what was the starting observation here is that using the kind of moves from fact 3, you will never be able to change the value at the extremes of this word, because this is the way the fact 3 works. So, but now that we have changed this is n prime, and this was n, I can do the same. Okay, using the same kind of thing, I get n prime 6 times. And if you check at each, if you do things quantitatively at each step, you look at how much you gain when you average with respect to your fixed point x0. You exactly get the Cauchy criteria that I claimed. I think that the difference between mu n and mu tilde n applied to x will be very small when x is very large, when n is very large, and this is, well, then you can again do the same mirror image to get back to mu, if you prefer, and not work on the other side of the mirror, and that's the end. Yes?
Sorry, something I missed a bit. So how did you get to n prime in the process? Because at some point you learned some stuff.
So the whole point.
How do you know that you are n prime?
So I was here. Yes. I said that this I can put it as low as I want. There's no here. The b and b prime they can be as low as I want. The constraint is that they cannot be too high. But here they are relatively high. I can put them wherever I want, and I put them not at value n but at value n prime. And of course, you have to tune a bit what is n prime, actually.
Yeah, n prime cannot be anything.
No, n prime will be 1.1 times n. 1.2 maybe, I don't remember exactly what the exact value of n prime is. But indeed, you prove that mu n and mu 1.1 times n will be very small. Well, you will be points, whenever you pass to mu n and mu n prime, you will get points that will be very close, and then you can repeat that it will be summable, and therefore it's Cauchy. Yeah. I'm already out of time, so I'm stopping now. Thank you.
Questions?
So this is an argument in rank 2. So in rank 3, how do you proceed along the bar complex?
That's a very good question, and I have no idea. So to prove the theorem that it did not write about arbitrary higher rank groups, actually you use the rank 2 reduction. You use that actually to prove the theorem. You only need to prove it for SL3 and SP4. For SL3, I gave you the proof. For SP4, what is good is that SP4 is also rank 2, so the root diagram is still two-dimensional, so you can still explore it in cyclically and anti-cyclically. So the analysis becomes much more complicated because the nilpotent groups that appear are not rank 1 nilpotent but rank 2 nilpotent, but still the fact that the picture is two-dimensional allows you to do the same strategy. I have no idea whether this kind of strategy can be made, we can give any sense to that for higher dimensional root systems. I don't need it for this theorem, but it could be an interesting question to try to understand what are the combinatorics of the root systems that you have to exploit in order to make this kind of things. I have no idea. Yes?
If you work with SL3, can you change A by different commutative ring?
The answer is yes, but it's not me. Oh, Oppenheim can do it. So actually but I don't remember if he gets the fixed point property only Banach space property T. So there is a distinction. You know, the Delorme-Guichardet theorem says that for Hilbert spaces, property T is equivalent to the fixed point property for isometric actions. This theorem is no longer true for Banach spaces, and at least the initial breakthrough by Oppenheim was that SL3Z has the property T with respect to every uniformly convex Banach space. And I'm sure that he can prove that if you take this this uniform, I don't remember the name. Well, these other rings.
Universal SL.
Yeah, universal SL3 of universal rings. I'm sure that he has property T. I don't remember if he has fixed point property. It's I should have known. I should know. I have known, but I have forgotten.
What about random groups of density filter and round there?
Maybe I'm confused with the rank, but aren't they hyperbolic? I think they are hyperbolic with high probability, and there is a classical result by you that they have how do you say, they have proper actions on LP spaces for P large enough. Of course, the P depends on the group, and it's known thanks to work of many people, including Cornelia, Claude, and John Mikael, that the P it goes to infinity, and it's I even expect that if you take random groups, they have the fixed point property with more and more Banach spaces, in the sense that if you fix uniformly convex Banach space, then when the parameter goes to infinity, a random group will have the fixed point property with respect to this Banach space. But the order of quantifier is important. You know that it's not true that for any of these random groups, they have the fixed point property with respect to all uniformly convex spaces. But if you reverse quantifiers, I'm sure it's true, but it's the precise statement that I said is still a conjecture. Yes?
Just to be sure, so when you said that he knows how to get the property for universal ring, you have to assume that the ring is commutative at the start. Because it seems that you are using the nilpotent things.
I don't remember. I can check on my computer right after the talk, but now I don't remember what it is.
Okay, thank you very much.
Thank you.